first live session. So the idea behind this sessions is to, basically go over some of the problems which a lot of you guys have been sharing on the Discord channel, or you've been personally sharing it with me, and then I want to debug that using the QuickSilicon platform itself. So that way we would have like a better idea of how to debug it, and in general we would learn different tips and tricks of how different kinds of error messages could be debugged and how we could make progress even if we don't understand the complete RTL or the architecture / microarchitecture. So that's what the idea is. And if you guys don't know me, my name is Rahul. I've been in the hardware design and verification industry for over 8 years now. And I run this platform called QuickSilicon.in, where I release practical hands-on courses around RTL design and verification. And these courses have helped people get jobs. Praneeth, he got a job in Apple, and he said, this course, helped him a lot in clearing the interviews. Vineet, he's currently working as a senior design engineer at ARM, and he also took the hands-on RTL design course. He left, a bigger testimonial, but he said that this particular thing helped him get better in his day-to-day activities. Because the kind of problems which I discuss here are very much related to the day-to-day activities you would face working as a design verification or just a design engineer, RTL design engineer. Right. So the idea today, what I want to do is I'll be covering 3 different problems, and we'll be covering one problem from the 21 days of RTL course, one from the processor design, and one from RTL design. And in each of these 3 different problems, we'll be covering 3 different types of bugs which are generally seen. So in this particular problem, we'll be looking at a FIFO design where we see an X-Propagation error, and we will see that how we would debug it and fix it live. In the processor design thing, this was shared by someone on Discord, where there was a 0 cycle combinational delay causing a hang in the simulator. So we will see that how we could debug those kind of fails on the QuickSilicon platform, and in general, even if you're using some of the commercial tools, how do you actually debug a 0 cycle combinational delay loop which causes a crash in the system. And finally, in the RTL design problem, we'll be looking at a difficult problem, but the idea behind that would be to basically, without understanding the complete RTL and the microarchitecture, which is generally the case, when we start working on a bigger project, we don't actually understand a lot of, the entire project per se, but we still have to debug a particular test failure and things like that. So without understanding the microarchitecture, the architecture requirements, we would still debug a fail and then try to fix it, just by understanding how RTL is written. And the reason why I want to do that is because I want to, basically emphasize that if you understand basic RTL constructs, that is good enough to get you started and make RTL fixes as well as debug things very quickly, right? So the order in which I will, yeah.
To interrupt, just a second. So there is a voice which is like after your audio, there is a bass that is coming in. So could you reduce that somehow?
There is what is coming, sorry?
Bass, a voice is coming after your voice.
Okay, is it better now?
Yeah, it's much better now.
Okay, cool, thanks. Yeah, so so this one is going to be the easiest one to look into, followed by the 0 cycle combinational delay, and then this obviously is going to be challenging because we don't understand what the RTL is supposed to do, and we will still debug it live. So yeah, let's get started with the first one. By the way, this is the 21 days of RTL challenge. This is freely available for anyone who wants to take it up. It has like 21 different problems, starting from mux going all the way to designing APB systems and stuff like that. So I'm gonna pick this synchronous FIFO stuff because this is where we're gonna dive deep. And like I mentioned, that we're gonna fix an X-Propagation error. The idea here is not to go deep into what the interface specifications say and how we are supposed to design it. The idea is that replicate what happens in the real world also. So if you run a particular test case, you are generally provided with waveforms, and So yeah, it comes up here, although it says that the test case passed because you're supposed to write the test bench and all the checkers yourself, and we haven't done that here. But if we take a look at the resulting waveforms, we see that the pop data is unknown when pop underscore I signal is asserted. So this is where the problem lies. So what is happening is that the pop data is unknown when the pop underscore I signal is seen, which means that FIFO is somehow giving unknown data on the output, which is represented by X here. The interesting thing to note here is that earlier when we had few cycles before when the pop was asserted, it was giving the correct data. So because if you take a look at the writes which were happening in the FIFO, we wrote 92, 40, 48, and the way we are reading out is, we read out 92, then 40, 48, 31, and so on. So this does seem to work in the correct fashion. It's 9215, so if we just zoom in here, so that's 9215. But after some time it starts giving excess. So how do we debug this? Generally for X-Prop, the way I approach it is to find the first source of X here, and try to backtrace it and see that okay, this particular logic is producing an X. But if you take a look at the waveform here, you don't see anything going X. So things seem fine, and suddenly X starts to appear on the pop data. We could take a look at the internal signals to understand a bit better. Just a second. Yeah. So if we take a look at the pointers as well, they seem to be functioning well. There is no X here, just the X is seen on the pop data. So would anyone like to take a guess as to what is happening here? Why do we see an X? I'll give a hint. So we see that it is working fine for the first few cycles, where the FIFO became full because we see the full flag getting asserted here, and then we started draining it out and we got the right data. It reached empty, but when it reached empty, after that it started to give X, even though if we see that there is actually something getting written into the FIFO. The push underscore I signal is asserted, the push data is also a known value, but when we try to pop that in the next cycle we get X. Would anyone like to take a guess here? I mean, feel free to take a guess as to why do you think we are getting an X when something like this has happened? Anyone? Okay, I'll try to take a look at this. So generally, if you understand how FIFOs are designed, is you would have like a block. Sorry. Yeah, so you would have like a block here, which is basically your buffer of the FIFO, and you would have like a write pointer and a read pointer. Generally, how these reads and write pointers are implemented is that as you write, your write pointer gets incremented. It keeps on moving ahead, and it wraps around to the top value again. So when it is wrapping around, the top bit or the MSB bit gets asserted. So if the MSB bit is getting asserted, then the pointer value is basically increasing the depth of the FIFO, which is why whenever you have to read from the FIFO, you don't actually use the complete pointer to address or basically mux out the read data. Instead, what you do is you basically read one bit less. And if we look at the code here, we could very easily see that the pop data, it is coming from the FIFO memory, but the FIFO memory is being addressed using the read pointer underscore Q signal. So since it is being addressed using the read pointer Q signal, we are using the actual pointer value. And if you take a look at how this is defined, it is defined as pointer width down to 0. But the FIFO mem is defined as depth minus 1 down to 0. And what depth is basically, the pointer width is equal to the C log 2 of depth, which means that this can go, the pointer actually includes the wrap bit as well. So if you want to basically read from the FIFO, you don't have to take a look at the pointer value, but actually take a look at pointer width -1 down to 0. So this would actually be ptr underscore width, and it is also read here. So let's change it, ptr underscore width -1 down to 0. So now what we are basically telling is, remove the wrap bit from it, but just read the value which is given by pointer width -1 down to 0, which would actually be the current pointer value and will not include the wrap bit. So if we run this now, we should not see any excess. Okay, something happened here. It is saying that line 63 has an error. Okay. Yeah, okay, so let me go full screen. And now if you take a look at the pop data, it is actually representing what the incoming data is. So we had 80 here, and then 80 is given back, 86, and then 86 is being read back. So yeah, so this way, we were able to solve the X-propagation. Generally, what people try to do with X-prop is try to find the source, but the source could actually be that you're trying to read something out from a particular array, but the index to the array is out of bounds. So which is what was happening here, and that is why it gave like an unknown value as the output. Like, any questions around this before we move on to the next problem?
Rahul, there was 937, which is the input value, right? And when
Mm-hmm.
the output, in the output, it was 93. Could that give the hint for us?
No. So actually, that's the problem with the waveforms. So
Uh,
if you zoom out, you would see the correct value. So it's not actually 80; it's actually a 4-bit value.
okay, okay.
Yeah,
Okay, okay, okay,
yeah,
okay.
yeah. So
Sorry, my bad.
no, that's fine. I mean, I also got confused when I looked into the waveforms because it was showing 9215 here, but the push was 92. So that's why I zoomed in a bit. But
Okay.
yeah, so yeah, I think generally how I approach this. So this was also one of the problems which was shared to me over WhatsApp by someone who was designing or doing this particular thing. And my first instinct was, because I understand like how FIFOs work, my first instinct was to take a look at what the read pointer value is. And although when I scroll down here, I was able to see that even though our FIFO depth is 8, the read pointer is becoming A, and at this particular point the pop data was unknown. So this was an indication that that particular guy is taking the entire read pointer instead of dropping the wrap bit and just using the lower bits of the read pointer to address the FIFO. Cool. Any other question? Great. By the way, I've seen similar sort of bugs in my day-to-day job as well, where a particular vector was being muxed out by a particular particular signal, where that signal was going out of bounds and leading to an X. And it did take a while for us to debug, because generally our idea in Verdi is to trace it back to the source, but when we reach here, we were unable to figure out like why is it giving X, even though this particular array contains all valid values. So yeah, just a tip that always check that what is the signal value within that particular array as well, and whether it is in bounds or out of bounds. Cool. So this was about the X-prop. The next one is the zero combinational delay, and this is one of my favorite problems because I've encountered this multiple times in my day-to-day jobs, where we add a new set of logic or a new set of test which is supposed to do something entirely different, and that leads to like a crash in the entire system. A lot of times, you produce the stack trace which gives you like some indication as to where the error is, but a bunch of times that is also not available, and you have to take a random guess as to what is happening. I'll generally, when those kinds of errors are seen, I try to basically look at the newly added stimulus and see like what RTL it is trying to touch at. By the way, this is part of the RISC-V processor design course. So this is not freely available. You need to subscribe to it in order to get access through it. And this is the problem which was shared on our Discord server. And someone who was at the final module, he wrote all of the code, he hit run test cases, and then got a weird error. So I'll hopefully it pops up. Yeah, so you can see that the error it shows is watchdog timeout simulator hung. Please check lint errors or look for 0 time delay feedback and circular logic. So although this is being done using Verilator, which sometimes gives you some indication as to where the error could be, but sometimes it does not. And in this case, it is not giving anything for us to debug. So it is just saying that there is a error and we should take a look at it. So this actually involves some understanding of the processor design. So but not a lot. How I debugged this was to I quickly went on to the top module, because I knew that this is the particular module after which the error started to show up, and then I started to take a look at what is happening. My first goal was to take a look at whether this all of since I know that the person has reached here, which means that the instruction memory, decode unit, register file, ALU, data memory, control, and the branch control units are working correctly, because those actually passed, and they did not, he did not see this kind of error when he was trying to run test cases on those particular modules. But at the moment he added, the code for the top level module, which basically includes adding a PC register, a mux for that, some adder, and few other muxes, he started to get this thing. And in order to understand, zero combinational delay is whenever you get, usually in hardware design we have logic, like we have a sequential block. Let's say this is the D flip-flop, and we have some combinational logic on top of it, and then we again have a flop. So this is what generally how the stages of different blocks are derived, or how do we pipeline in general. Now a lot of times the combinational output can also be fed back to the same D pin of the same flop from which we are utilizing the Q output. So this also works and is fine, but the combinational delay or the zero feedback loop exists when you are actually trying to take an output from a particular combinational block and trying to feed that back in. So this is the scenario under which the simulator hungs, because you're trying to calculate a new value after certain combinational logic, which is all of this actually happens in zero time as far as the simulator is concerned. So this is the reason why you would hang. And if you take a look at the top level module, the place where this could happen is basically somewhere here, because you are trying to produce something, you are trying to produce the new PC value, then flop it to a particular register and then use it ahead. So this was my instinct on how to debug this case. And when I looked into his code, I quickly went into how his PC register is made. And you can very clearly see is that he's using a combinational block for his PC register instead of having an actual flip-flop. So the fix here would be to just change this PC reg to be a flop rather than being derived combinatorially. So how do we do this is, we could, let me change this to Vim. Yeah. So the PC count is something which is basically the next PC count, and this ideally should have been, the registered value. So let's call it PC underscore Q. Change this here as well. So this would also be PC underscore Q. And the next value which this will feed will come from, the entire mux logic here, which we have, which is basically this statement. So let's do that. So instead of PC count, this would be PC reg. And let's change this count to be reg. And we have removed count, so this would again be reg. Okay. This would, sorry, not be reg, this would be PC underscore Q. So what we are basically trying to do here is the next PC value is basically driven through this mux, where it either picks the whatever the incoming value is, which is this, or it picks the the added value. So we need to do the addition here as well. So this would become 32 tick edge 4, and we don't have to do it here. So now this particular logic represents exactly what is shown here. And let's just clean it up a bit. So this is, instead of PC reg, we will use the flopped value everywhere. So this would be PCQ. This would again be PCQ. And this would again be PCQ. Cool. So now hopefully this should go away. So if you hit run test cases now, it's saying PC reg duplicate declaration. Okay.
No, PCQ not different.
Right. Thanks for that. Yeah. And now, yeah, it does work, but yeah, both the test cases are still failing. So at this point I stopped because I wanted that person to debug the reason of failure instead of me going ahead. But this is how I actually approached it, and this happens a lot in real world also. Trust me, in the past 2 years at TenStorrent, I've seen bunch of these cases come up and show up, and people they tend to spend a lot of time looking at various other things, blaming the simulator or things like that. My goal is to always look at the simplest thing which is happening, and try to read up and see how the architecture is driven and whether it actually matches to what we are trying to implement. So yeah, this was something which I was able to do it. And in fact, even before I shared this, the guy was able to figure it out and get it to work, because this picture, this does help. So cool. So any questions here, anything which isn't clear, or something around that? Okay. Yeah, going on to the next one, which is something which will again be very realistic. This is part of the RTL hands-on RTL design course, and a lot of people actually do this daily. And every week I get like a bunch of problems around this. Sometimes the test bench is incorrect, sometimes the RTL code is incorrect, but it's been fun going through the problems which are being shared on Discord and stuff like that. So the thing which we're going to look at is basically the credit and deadlock problem. So this is a hard problem, but again the idea is that we don't understand what this particular problem is trying to do, because a lot of times that's what the reality is. We get onto a project which is basically halfway there, and then we don't understand how it works completely, but we are still supposed to debug things, fix those test cases which are failing, and file RTL bugs also, where obviously we don't understand the entire intent or the microarchitecture of a particular thing. So this is what I wanted to do with this particular debug help, that we will run it, we will see some functional errors, and we will try to debug as to why this particular test case is failing. We will pick the test case 1 here itself, and let me go full screen. Right. So the first thing which we will do is, what is the error? So the error it is trying to say is that no ready or retry seen for 3 cycles. So, okay, so this does not seem to make any sense right now, but let's quickly take a look at what the spec is saying. So let me close this, and yeah, so one thing which the interface requirements say is that the request on the RX channel must either get a ready or a retry in 3 cycle window. Okay, so this does seem that the check is correct, so we can rule out that the check is itself incorrect, but we still don't know whether it is implemented correctly or not. So we will try to figure that too, but yeah, the check is correct. Let me get back the waveforms. Okay, so we figured that the check is correct, and it is saying that no radio retry seen for 3 cycles. And generally when something like this fails, you would have to look at the last transaction which is happening. So on the RX channel, the last transaction was, it started on this particular cycle because we got a retry for this particular transaction, and this did not fail the check. So if you take a look at this, the next valid, which is on the next clock cycle itself, the retry comes here and it takes actually 1 clock cycle extra, because if you count the number of clock cycles, it is 1, 2, 3 and 4, which is why the check fires that we should have seen the retry or ready coming at least in the 3 cycle window, which we do not see happening. So how do we debug this without any RTL design knowledge or something like that, is to basically try to follow as to what is happening in the previous passing transaction. So if we take a look at the previous passing transaction, we do see that we have a valid here, and the retry comes in 3 cycles. So let's try to take a look at how the retry logic is driven. So let me close this as well. So yes, the first thing is ready. So the ready is driven using some counter value where it says that if the count max is not seen, then keep the ready asserted, or if it's a retried request. And the retried request is dependent on a valid with a credit. So if we take a look at the waveforms, we do not see the credit signal getting asserted anywhere. So this means that this particular thing will not get asserted. And let's also check the value of RSP count max. What is that? Okay, yeah. RSP count max. Yeah. So here it does get asserted here. So which means that the ready will not be asserted. And the reason why we can say that this is the correct behavior is because the previous transaction which got a retry got passed the the checks. So this is the reason why we know that ready getting deasserted here is probably correct, and the retry here was the correct thing to do since the check passed. So now on the next cycle, the retry is again getting asserted, but it is taking an extra clock cycle, which means there's something wrong happening with the retry logic. So let's try to take a look at the retry logic itself. So the retry gets asserted when we have like something called as like a deadlock enable signal asserted, the FIFO is stalled, and there is no credit. So we did have a look at the credit thing, it was not asserted. Let's check RX FIFO stalled value, whether that is asserted or not. So the RX FIFO stall is also asserted, so which means this condition is also met. Then the general idea is that both of these conditions are true, then the deadlock enable thing is not getting asserted. So why is that not getting asserted is because and the way it is getting asserted is that the deadlock count should be equal to 2 tick B10. We did see that happen before, so let's take a look at the count value when it got asserted here on this particular cycle itself. So yeah, so the deadlock count was 2, it did got asserted, but then on the very next cycle it went to 3, then again 0, 1 and 2. So this probably is the place where you would know that something is going wrong with this particular deadlock counter, but you still don't know what is happening. But yeah, something seems incorrect here, because the last time when the counter worked, it was able to reach to a value of 2 and assert the retry signal at this particular clock cycle, and that happened to be within the 3 cycle window of which we were trying to which basically the interface specifications tell us to do. But on the particularly next scenario, it switches to 3, then again 0, 1 and 2, which is why it is taking like an extra clock cycle by going to value of 3 and then 0, 1 and 2. Had it been reset to 0, then also it would have worked correctly, because in this particular cycle this is the case when the first clock edge of valid is seen and the counter value is 0. So this does make sense that if it starts from 0, it will reach to 2 within the 3 clock cycle window, and if the retry conditions are met, it will get asserted. So that is one way to fix it. The other way could be that we could think more as to if we are already in a situation where we are giving retries, then let's check when the counter gets reset to a value of 0. So if you take a look at that, there is one condition here in the RTL which specifies that whenever RX-FIFO pop happens, then the next value of the counter should be 0. If the RX-FIFO is stalled, then we should add 1 to the counter. Otherwise, we should keep the same value. And in the waveforms, we saw that the RX-FIFO stalled signal is always 1, which is why the counter was getting incremented right on this cycle. So one way to fix it would be whenever the counter has reached the value of 2TIC-B10, that is deadlock enable is asserted, we should not increment the counter anymore, or we should freeze at that particular point. And such counters are designed, and those are designed as part of the 21 days of RTL series as well, where we call those as like the saturating counters, where if they reach a particular value, you just saturate there, and some other condition in the combinational logic would bring it out from that saturated value. So that's how we could fix this. If we just add like a condition here, which is if deadlock enable, then keep the current count value. So which is deadlock underscore count underscore q. Let's just align it correctly. Yeah. So now what we are trying to say is if the deadlock enable was set, then keep the counter value same, and some other condition, probably RX-FIFO pop condition, would make the counter 0 the next time. So this is basically saturating the counter. This is resetting the counter. This is incrementing the counter. And if none of that happens, then keep the same value. So if we run with this fix, that should hopefully fix the 3 cycle window of which we've been worried about. Yeah, as you see now, all of the test cases pass, but it's good to take a look at the waveforms once again to see if the retry is indeed getting asserted. So now you see that the retry behavior, it changed drastically. So this was the first transaction which got a retry, but then afterwards, all of the other transactions, they get retry in the same cycle itself. So this is because we added the saturating counter. And let's take a look at the counter value too. So the deadlock count, once it becomes 2, it stays at 2 forever. So yeah, that's one way to fix it. I did not look into the RTL microarchitecture and stuff like that. Just went through the interface specifications a bit, so to understand whether the check makes sense or not, and made the RTL fix by taking a look at what the RTL is trying to do. So obviously I did have some background of this, but I still believe that you should be able to debug problems by just looking into different smaller blocks within the RTL and trying to understand that behavior and trying to rule out certain conditions. When we looked at retry, we first figured that the retry getting asserted was the correct thing to do since it passed the previous check. But on the next transaction, it was failing, which generally pointed us to something going wrong with these set of signals. We confirmed that credit is correct, FIFO stalled is correct, but deadlock enable had some issue, which we were able to fix it, by looking at how this particular counter is implemented. So, this is how I actually approach larger projects too, that I try to distill the problem down to few RTL blocks. By RTL blocks, I mean RTL constructs like counters, FIFOs, buffers, or, arbiters and stuff like that, and then try to debug it closely from there. Yeah, so this is what I had planned for this particular session. Are there any questions? Anything else? Do you guys want to know about QuickSilicon? Feel free to discuss. Since this was the first session, I expected that not a lot of people would contribute, but in the next sessions which we are planning, I would appreciate if it is community driven and it is interactive, because I would want to take up more questions from you guys, the problems you guys are seeing, and then debug it live rather than I picking up a problem and then solving it. Any questions, guys? Yeah, if no, then that's what we had. Thank you for joining in on a Saturday. Yeah.
Yeah, thanks, Rahul.
Yeah, thanks for. I hope this was useful.
Yeah, thank you.
Thank you. All right. Thank you, guys. Thanks for joining. Have a good day. Enjoy the weekend.